Two of the most powerful telescopes ever built, one designed to scan the entire sky every few nights, the other designed to star-E deeply at a single target and read its chemistry, ended up studying the exact same object without ever planning to. Neither one was built with this specific target in mind. Both found something genuinely strange about it anyway. Stick around, because I'm about to walk you through exactly how James Webb and the Vera Rubin Observatory each contributed a completely different piece of the same puzzle, what that combined picture actually revealed, and why this kind of accidental teamwork between two very different telescopes is becoming increasingly common in modern astronomy. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. This particular object's story is still being pieced together. Let's start with what these two telescopes actually are, because understanding how different they are makes the rest of this story make sense. James Webb is a space-based infrared telescope positioned nearly 1 million miles from Earth, built to stare deeply and precisely at individual targets, capturing detailed chemical fingerprints from objects billions of light years away. The Vera C Rubin Observatory is something almost entirely different, a ground-based telescope in the mountains of Chile, built not to focus narrowly on single targets, but to scan the entire visible southern sky repeatedly every few nights for the next 10 years, as part of a survey designed to catalog literally billions of objects. One telescope reads chemistry in extraordinary detail. The other one watches practically everything, constantly, and flags whatever changes. The technical specifications behind each telescope explain exactly why they ended up playing such different roles in this story. Webb sits at a gravitationally stable point called L2, nearly 1 million miles from Earth, using a 6.5-meter primary mirror and a suite of infrared instruments specifically engineered to isolate faint chemical signals from individual objects, even ones sitting billions. An 8.4-meter telescope feeding into the largest digital camera ever built, roughly the size of a small car, containing more than 3 billion pixels, engineered specifically for breadth and speed rather than narrow extended focus. Where Webb might spend hours or even days studying one specific target in exhaustive detail, Rubin captures an enormous swath of sky in a single exposure before quickly moving on to the next patch, repeating that pattern across the entire visible southern sky every few nights throughout its 10-year mission. If you're the kind of person who wants space discoveries explained clearly instead of buried in jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. The object that ended up connecting both telescopes is 3I Atlas, only the third interstellar object ever confirmed passing through our solar system, discovered on July 1st, 2025, when an automated sky survey system called Atlas spotted a faint object moving on a trajectory that made no sense for anything born in our own solar system. Astronomers confirmed within days it was simply passing through on a hyperbolic path stretching back across the galaxy, following Oumuamua in 2017 and Comet Borisov in 2019, as only the third confirmed visitor of its kind in recorded history. Each of these 3 interstellar visitors taught astronomers something different, and understanding that progression helps explain why 3I Atlas generated such an enormous coordinated response across the astronomical community. Oumuamua, discovered in 2017, was gone before researchers could gather anywhere near enough data to fully characterize it, leaving behind more questions than answers and years of ongoing speculation about its true nature. Borisov, found in 2019, behaved much more like a familiar comet, giving astronomers their first real chemical comparison point between an interstellar object and objects native to our own solar system. By the time 3I Atlas arrived in 2025, astronomers had learned enough from the previous 2 visitors to mobilize an extraordinary coordinated observational campaign almost immediately, determined not to let this third opportunity slip away with as many unanswered questions as the first one had. Here's where Vera Rubin's contribution comes in, and it happened almost entirely by accident. Months before Rubin's official 10-year survey had even formally begun, the observatory was still working through its commissioning phase, running engineering tests to calibrate its systems ahead of full scientific operations. During those routine tests on July 3rd, 2025, Rubin's camera happened to capture images of the exact patch of sky where 3I Atlas was sitting, Taurus, days before anyone else had even formally announced the comet's discovery to the world. If you found this as fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. Nobody realized what those test images actually contained until months later. A team, led by researcher Colin Orion Chandler, went digging back through Rubin's archived commissioning data, specifically hoping to find exactly this kind of unplanned early observation, a process astronomers call a pre-covery search. They found it. Rubin had unknowingly photographed 3I Atlas before the world even knew it existed. And because Rubin's specific processing pipeline for tracking fast-moving solar system objects wasn't fully operational yet at the time, the team had to build custom techniques just to properly analyze data the telescope was never specifically tuned to capture. The effort paid off. Using those unplanned early images, researchers extracted precise position, measurements that helped refine the comet's orbital calculations, gathered detailed brightness data, and studied clues about the structure of its nucleus, all published in the Astrophysical Journal Letters in 2026. This kind of pre-cover research has become a standard part of studying any newly discovered interstellar object, since finding earlier images taken before the official discovery date can dramatically improve how precisely researchers calculate an object's orbit. The longer the observation baseline, meaning the more time separates the earliest and most recent images of the same object, the more accurately its trajectory through space can be calculated, and the more confidently researchers can predict exactly where it came from and where it's ultimately heading. For an object as rare and scientifically valuable as an interstellar comet, finding even a single additional set of images from days before the official discovery genuinely matters, refining calculations that every other research team studying the comet, including the one working with Webb's data, would go on to rely on. Archives like Rubin's, growing by tens of terabytes every single night, are now effectively permanent records that future researchers can search retroactively whenever a new object of interest gets identified, turning routine engineering data into genuine scientific value months or even years after it was originally captured. While Rubin was unknowingly gathering that early data, James Webb was doing something completely different with the same object, once astronomers actually knew where to look. Webb's first observation came on August 6, 2025, using its near-infrared spectrograph to read the comet's chemical fingerprint directly. That early data already showed something worth noting: 3I Atlas, releasing considerably more carbon dioxide relative to water than typical solar system comets. But the most important observation came later, after the comet made its closest approach to the Sun on October 29, 2025, when the heat finally cracked open billions of years of frozen chemistry that had been sealed inside the comet the entire time. Webb's follow-up observations in December 2025, using its mid-infrared instrument, revealed methane, the first time this specific gas had ever been confirmed on any interstellar object, at a ratio roughly 11 times higher relative to water than anything found in comets native to our own solar system. Alongside that came something researchers still can't fully explain: a clear signature of nickel vapor detected under conditions where nobody expected to find it on an object this far from the Sun. Using all of that chemical evidence, a team published findings in the journal Nature in June 2026, concluding the comet's ice likely formed in an environment colder than 30 degrees above absolute zero, in a region so ancient that 3I Atlas is now estimated to be somewhere potentially older than our entire galaxy's oldest known stars. The timing of that December observation window mattered enormously for how much Webb was actually able to detect. When 3I Atlas was first discovered, it was still faint and far from the Sun, giving off very little gas for any instrument to analyze in detail. But after the comet swept past the Sun during its October perihelion, the intense heat cracked open billions of years of frozen chemistry all at once, converting a substantial portion of the comet's icy exterior into a bright, glowing cloud of gas. Astronomers specifically waited for this post-perihelion window to turn Webb back toward the comet, capturing detailed measurements, while that surrounding cloud of gas was at its most active and most chemically revealing. Missing that specific window would have meant missing the methane detection entirely, since the gas simply hadn't been released yet during Webb's earlier August 2025 observation. So here's what actually happened when these two completely different telescopes' contributions got combined. Rubin's accidental precovery images extended the observational timeline for 3I Atlas backward by 2 full days, improving how precisely researchers could calculate its trajectory through the solar system. Webb's spectroscopy read the actual chemistry locked inside the comet, revealing its extreme age and its genuinely unusual composition. Neither telescope was specifically built to study this particular object together with the other. Rubin caught it by accident during equipment testing. Webb was deliberately pointed at it once astronomers already knew where to look. But the combination of both datasets gave researchers a considerably more complete picture than either telescope could have produced working alone. It wasn't just these two telescopes either. Because interstellar objects are so rare, and because 3I Atlas was only passing through once, NASA mobilized an extraordinary range of additional spacecraft to study it while they still had the chance. Hubble captured what NASA described as the sharpest ever picture of the comet in July 2025. The European Space Agency's JWST mission, originally built to study Jupiter's icy moons, pointed 5 separate instruments at the comet in November 2025, later measuring water production rates considerably higher than expected for an object this size. TESS, SWIFT, Sphere-X, the Perseverance Mars rover, MAVEN, and several other missions never designed with interstellar comets in mind, all contributed observations during the brief window this object was actually passing through our solar system. Rubin and Webb's combined contribution was really just two threads in a much larger, genuinely unprecedented coordinated effort spanning more than a dozen separate spacecraft. This kind of unplanned collaboration between fundamentally different telescopes is becoming an increasingly important part of how modern astronomy actually works. Rubin's wide, repeated coverage of the entire sky means it's now constantly generating an enormous archive of data covering essentially everything visible from its location in Chile, including plenty of objects nobody has identified as significant yet. Webb's precision means that once something interesting does get flagged, whether by Rubin's automated alert system or any other survey, it can be studied in extraordinary chemical detail that a wide-field survey telescope was never designed to provide. Neither telescope replaces the other. Together, they're increasingly functioning as two halves of the same overall discovery process, one casting an enormous net across the sky, the other examining whatever gets caught in it with much finer detail. That complementary relationship is likely to become even more significant going forward. Now that Rubin's alert system is fully operational, capable of flagging up to 7 million changes across the sky every single night, astronomers expect to identify interesting new objects, including future interstellar visitors, considerably faster than the roughly once every few years pace at which Oumuamua, Borisov, and 3I Atlas were each discovered. Researchers studying 3I Atlas have already calculated that objects of similar size likely exist in far greater numbers throughout our cosmic neighborhood than previously assumed, simply too faint or too far away to have been detected until instruments like Rubin came along capable of systematically searching for them.